Hello and welcome back to Compiler Programming. It has been a while since the last episode, but I'm finally back and ready to work on the compiler. Between this and the last episode, not much have actually changed, but there were a few minor changes here and there, so if you're interested, please check the repository. I will link it in the description below. But for today, what I was thinking of doing is that one thing that really prevents me from using the compiler is the fact that I can't really debug anything that goes wrong from within the compiler, and already had this thought, so at some point I started to work on this debugger, and I might link that episode as well. However, the issue is that it's not very useful. If we try to sort of run an example that has a breakpoint, as you can see down here, we have output, right? We hit the breakpoint, we opened up the debugger, but in here there is limited stuff that we can do. Right now I can print locals, and this is something I actually finished off camera recently. This was working at some point to a degree, but there were a bunch of issues and I just fixed those. Now it works pretty nice. To see that it actually shows the right thing, I can go to the source file here, and you can see that's what it looks like. So we can see we have a variable I, we have a message, we have the process and IO, and right now locals sort of prints all the variables that are defined within one scope. So if I do something like this, I believe it should actually only print I. Let's check. Locals. Yeah, so it only prints I, which is actually what we are interested in for today, because I want to be able to actually print that value. Obviously right now it's easy to see that it's 42, but that's not necessarily the case in general sense. Like even here we can say, for example, 21 times 2 or something, right? And well, apparently that doesn't work. But let's say 21 plus 21. Okay, right. So we would like to see that it did and equal to 42. But if I say print I say to do support printing of values. So that's what we want to work on. Eventually, I would like to support like custom printing of values, but that's definitely a topic for today. For now, I want to be able to just like, same as basically in GDB or in debugger, you just dump the raw fields of struct, or just dump the value if it is an integer, right? So that's what I want to do. And yeah, just let's get started. Win32 runtime, this is the code that is responsible for this. We see this line here to do support printing values. I can close this out. I don't need this right now. And the question is, so what do we do in here? Well, let's just say mass debug. I can type today, print value, and I will pass a value, right? So that's what I'm going to do. I'm going to take this, I'm going to implement it. Static void mass debug print value. Okay, great. And we're going to say value, right? Okay. So what do we need to print the value? Well, there are sort of two parts to it. We need to know where it's located in memory, and we need to know what is the type, so we know how to sort of print it, right? Let's start with the first one. We can say const storage star storage is value. Yeah, okay, so that's the first sort of thing that we probably should only get forced values in here, so let's assert on that. And what forced means is that we actually have a explicit location for it. We have explicit storage. We shouldn't really get lazy values, I think. But if we ever get to, this is sort of trigger, and then I can look into it and figure out what to do about it. Okay, so we have a storage. Great. Now we need to actually get sort of memory from that storage. So let's do that. We say const void star memory is, I don't know, we don't know what memory is. We'll look at the storage tag, and as you can see, I'm actually switched to using C-line for my editor because it offers a bit of convenience here and there, which is nice. I will actually want to go back to my own editor as I did before, but that's gonna happen later. Okay, so just preparing some nice stuff here. Let's go for it. Okay, if it is an immediate, that's actually probably the easiest case, because that means that the value is stored directly in the, well, value storage, right? So we can do, say, memory, storage, immediate, and bits, and just sort of point to that. That's pretty straightforward. Okay, if flags registers XMM, I think yeah, we actually have them in context record. We just need to get them out. Eventually I might store it in my own struct here, but for now that's not really important. So let's pass the context record, and what it is, again, you can watch one of the previous videos where I actually implemented this handler, but the thing is, whenever on Windows, at least, when you get an exception, you can set up a handler for that exception on the sort of system level, not the language level, and Windows will call that function whenever exception happens and provide you this context record that contains a bunch of information. And some of the information is actually the state of the registers at the point where the exception happened. And breakpoints are sort of user-triggered exceptions, if that makes sense. So in here, what we can do is we can say memory is going to be actually context record iflags, right? Do I need to do something in here? Storage, iflags. Yeah, okay. So I need to actually look at the compare type, but for now we'll just say to do like this. That's okay. Register is more of the same. The only unfortunate case, I guess, here is the fact that we will need to map the register that is from here. Oh, we also have 17 bits. Yikesy. Okay, whatever. Let's say like this, and we can again generate a bunch of these cases. I think this should only happen in here. Yeah, I think so. So I think it should be actually like this, and that's XMM index. Right, and it complains that it's unhandled, so let's say default, printf, let's just assert. Assert not unknown register or XMM register index, right? So that's the default case. We can put it in here. We can remove this stuff. And now we just need to do a very annoying thing. That's basically this thing. Okay, this is gonna be rux and a bunch of stuff over here. I should copy this stuff. Let's quickly do that. So RCX, RDX, RBX, RSP, RBP, RSI, RDI, R8, okay, R9, R10. Not very exciting content, but you know, it has to be done. Because the problem is I can't really guarantee that these fields are in the same order, and then doing some kind of, pointer arithmetic or something on it, that's just not really worth it. Let's properly map it, and we have to just do it once. It's okay. In here, there is basically more of the same. Maybe I can use the power of I can use the power of multiple cursors and say context record and XMM 0. We still need to provide numbers. I guess I could have done the following. So what I could do is do really great. It's fine. Let's do that way. And then we can do like this. Okay. Some fancy multiple cursor stuff here. We say here general purpose. So we know what happens when we hit this breakpoint. Hopefully we never. Right. Well, that was not very smart of me, because I also need to put in memory, and that's not great. Let's try that again. Okay. Now it's good. So we can get the register, we can get XMM. Static is really screwed up, I think, because we need to figure out how to map the memory. I'm not gonna deal with it right now. My goal for today is just to be able to get the just print that I variable that we saw, and that's actually probably on the stack, so it will fall into this case, I think. And I'm just gonna ignore this static, because it involves a bunch of acrobatics with memory and trying to chase where it is actually in the program. Support static storage, and let's just return. Okay, and that's basically the same for disjoint. Disjoint is even more funky, because this is the storage type I use for dealing with the fact that in systemv calling convention, so on Linux, whenever you pass a struct that is 2 register wide, it ends up being split into 2 registers, and then you have to like deal with it if you want to load the whole struct back into something, for example. So like it's a bit annoying to deal with, but this is what it is, and I don't care enough for now. But eventually, of course, this needs to be fixed. Disjoint storage. Okay, now we have storage tag memory, and memory is actually unfortunately also has multiple things. So storage memory location tag, right? And it has another 3 options, which are the following. Rip relative, I don't care enough about for now. Because again, I will have to deal with like labels and stuff. And this is only important maybe for functions, but not important enough for me to care about it. So to do rip relative interesting. Okay, indirect and the stack. Actually, that reminds me of something that I forgot. That memory, because in register we actually have. So if we look into the storage register, yeah, you have offset and bits. I don't actually even remember what the pact is. Doesn't matter. Offset and bits allows us to say that we are pointing to a part of the register. So I need to take that into account, and I guess I need to say that. Well, first of all, I need to assert that %8 is 0. So we only support byte aligned stuff, right? And then here I can do this, and I want to move the memory by that offset. So I need to say memory plus, but unfortunately in here I also need to convert it to U8 star, because otherwise it will use different like wrong offsets. So that sounds good to me. And I'm pretty sure we will need to do something similar in here. But let's start with this stuff. Okay, so const storage. Is it memory allocation? Yeah, okay, memory allocation. Indirect is storage. Memory allocation indirect. And what do we have inside indirects? We have offset and we have base register. Yeah, so we need to do the same adjustment, but I guess I need to, right, I need to take this out and put it into a helper. So static, I don't know, const void star. Insert to debugger register memory or something. I don't know. We need to pass in the register reg. Okay, and we also need to pass the context. What was it called? I'm just gonna copy paste it. Context record. Okay, and I guess we need to replace this stuff with return. Right. I don't know if we need to do this. Let's see. If it understands that assert sort of explodes. Actually, it might only explode in optimized builds, so that's neither here nor there. But what we can say is memory is context record, and then we also need to pass in storage register index. That is good. Okay. Right. And now we need to do the same stuff with in here, but we're gonna take it in indirect base register. Base register. And then we need to do the same adjustments in here, except the math is slightly different. We'll take the indirect stuff and we'll say indirect offset. Sounds good to me. Hopefully stack is basically more of the same. So let's start that. Stack, and then I say stack and stack. Okay. Sorry, my nose is very itchy for some reason. Stack is stack area. Stack area. Oh, right. right. So what we're going to do is say switch on stack area and add a bunch of to-dos here as well, because the problem here, like, we should never get in here, I think. So I can say assert this should not get an unexpected call target argument stack storage. So the reason this shouldn't happen is because this particular encoding happens when we want to put something on the stack for the target function, and there is no way to refer to that value from the source code. Like, that value is only created temporarily by the compiler internally, and so we should never actually see it in a debugger, I think. But who knows? This stuff can happen, is sort of the opposite side of it. So whenever you receive an argument and that argument is being passed on the stack, you need to figure out how to get to it. The trouble here is that offset calculation is going to be screwed up, because you need to know like what was the final stack size of a function, and I don't know if we can easily get to that. So for now, again, this happens to be a to-do support stack argument storage. This is the one that we are actually interested in for today, I think. And yeah, it should be more of the same, right? So we do this, we say, actually, we know which register it is. It is register SP. And in here we say stack offset. We might need to do it in opposite direction. Hopefully not. We'll see. Yeah. So, I mean, that's great. We got the memory. We can even try to run this, I think. Apparently we can't because, yeah, okay. Because I'm not passing context record. Okay, we can run it. We can try to do print I and nothing happens, because, I mean, that's actually good that nothing happens. Means we passed through this whole thing and we found the right, or something that looks like a right memory. But now we need to deal with the second part of this, which is what exactly? Which is the descriptor. So let's do that. Descriptor star descriptor is value descriptor, and more of the same. We switch on the descriptor tag, right? Create missing switch cases and start working on that. So, another thing we probably want here is the size of this whole thing. Because if it's void, we should check that it is, yeah, descriptor by size of descriptor. So in here we can assert that descriptor, or no, sorry, byte size is 0. And then we can printf, I don't know, void, whatever. Doesn't matter. And the same basically in here. I'm not even sure we should ever see never types. I don't know. Let's just say it is okay, and I think it also should be zero sized. Raw is basically bytes directly. How do we want to do that? I mean, one way would be to just print them, right? Why not? We can say raw and then like this, or like this, or like this. Right? And for I0, I is less than byte size, right? And we can just say printf, and what it will look like. Percent 0 to x or something. And here I can say char. Well, something like this. So just read the memory and print it out. I guess in some cases you would want to flip them around in the sense that like if it's treated as an integer, it should be in forgot what it's called, but basically in reverse byte order. But again, it's fine for now. Whatever this prints, it's already better than not printing anything, and then I can refine based on actual troubles I potentially encounter when trying to use this. Float. Well, it's again the same thing. So I think C actually widens floats to doubles all the time. So I think this should work. But if not, that's okay. And else, well, I can say unknown supported float byte size or something. Like, I don't think I encode floats of any size other than that, so this should be pretty safe, at least for now. And later I can figure out if that's what I want to do. So here I can say printf and percent %f, and then I guess double star memory. Okay, no, that's not correct. So I do need to split this up. I need to say else if byte size is 4. Yeah, but I was right that it's okay with f. Okay, those are floats. What do we have next? This stuff I will just do, to be honest, because this will require something like recursion, and I'm not ready to work on that just about now. Again, the goal for the day is to print that 42 and be happy about it. So let's try that out. Support pointer types. And same for structs, support structs and arrays. We might do it as a separate video later on. I'll see how I feel about it. Maybe I'll do it off screen. Who knows? Maybe video is better. Okay, support function instances. I think I actually already have code to print functions, more or less, that I use for errors. So maybe I can reuse that. But again, let's later, and let's do integers. Integers. So the thing with integers is that they are either signed or unsigned. So I guess I need to do like something like this, right? And then say default, you know, this kind of stuff. Unsupported integer. I don't know what is the better option. I mean, I can actually do it slightly differently, because for integer printing, at least the way just printing number without padding or something, we don't care what the size of it is. So maybe I can say if byte size less than 0, less than 1, or byte size more than 8, then we have a problem. No, that's not gonna work. No. Let's continue as we did before. And we can say case 1, break, and then we say printf %. I have to do something like pre-u8, right? And then, well, this stuff. Here, 2, 4, 8. There might be a more, elegant way to do it, but again, I don't care at the moment. And also, this might still be more robust than what we had before. 32, 64, 64. And this is not 5, this is 8. 1, 2, 4, 8. Sounds about right. And I guess the same stuff in here. The only difference is that I need to do S. Actually S, and then S in here. I mean, that doesn't look that bad. Let's see if that compiles. It does compile. So, moment of truth. Let's see what happens if I do print I. Well, I mean, sort of. So there are a couple of problems here. Problem number 1 is a new line, which is the easiest to fix. Let's just do that. The second thing is, I think I actually want to switch it to like this. Then we also want to probably have spaces between bytes. So const char star space is I is 0, then this, and then otherwise it's this, and then I can do %s, and then say space. Can also do a separate printf, doesn't matter. I'm just kind of used to this stuff for some reason. So that should be better. Obviously, if it works, then it should be better. Oh yeah, missing a semicolon. And let's do print I. Yeah, so this is what I was talking about flipped byte order, because okay, so what happens here? Let me explain a bit. Right now in mass, these numbers are not actually signed or unsigned integers, they are raw. I'm not sure, like I implemented it, it sounded like a great idea at the time. I'm not sure it's actually a good idea, but it is what it is, so they are raw. And so we are printing it correctly. This is 42 in hex, however, it is sort of flipped other way around. And yeah, but I guess it's fine. I need to think about what I want to do with this. Maybe I want to for this to be not raw, or I want to introduce something like, I don't know, print as, or I don't know. There are options of how to deal with it. For now, what we can do actually in here is say print S64, and that should force it to be a number. So let's try again. And another thing I want to do is have history. Maybe it sort of exists. Let's see. Yeah, so this is great. We have 42. I guess the question is, can we print negative numbers in here? So let's say -21, -21. And then we say print I. That does not seem like the right answer to me. What did go wrong here? Well, it's other way around. So let's try again. Print I. And we have a 42. Great, great. Yeah, there is obviously lots left to do here. There is lots to do with storage. There's lots to do with the printing of various types. The raw thing is a bit awkward. But yeah, I like it. I think it's progress, and I think this is where it would be a good time to wrap up for today, and hopefully see you next time.